Hello all. In this video, I'm going to talk about, I'm not going to talk, but we'll try to see how we can solve a problem with the help of a CDF function. In the earlier video, we have discussed about inferential statistics and descriptive statistics, right? So let's understand some of the formulas and we'll try to solve a few problems, right? So with the help of a central limit theorem, right? Let's look into this. So whenever there is a normal distribution, if the data is distributed normally, so basically, however you take the samples, right? Let's say that you have a population, right? Population, you have all the data, right? And you take, however, the sample from this population. So say this is a sample, right? So you plot this sample data, still it looks like a normal distribution only because my population is also normally distributed, right? The sample from the normal distributed population still looks a normal distribution only. So that is what I'm trying to say here. Normal distribution. Distribution is always normal irrespective of sample size. All right. And there is something non-normal distribution, right? Say that let's delete this. Okay. Suppose say that I have a population distribution looks something like this, right? Which is not a normal, right? So, but what I will do, I will take some sample data from this non-normal distribution. So I will take a few samples, 1, 2, 3, 4, up to 30. All right. So if sample size is adequate, when I can say a sample size is adequate? So the guideline says that if the sample size is basically greater than 30, right? So then we can say that, okay, it's adequate, right? If you take an adequate sample size, then distribution starts looking normal. So how is that? Suppose say I have taken a sample size here. So what I will do, I will take a mean of all these samples, right? These are the sample. And what I will do next, I will take a mean of sample. Okay, I will get a mean of sample, right? And if I take again mean of sample mean, right? So first of all, this is my sample and I will take a mean, and mean. And I have one data, right? I will get a mean of each sample. Again, if I take a mean of these guys, I will get one mean data, right? So that mean is basically what? A population mean, right? So in that case, how it looks like, let me draw here. So first of all, when I take a sample and I try to plot a graph, so what happens? It slowly looks like this, right? Again, I take a mean and plot a data. So it is something like this. And if I continue, so slowly it will start looking like a normal distribution, right? So that is what I'm trying to say here. If sample size is adequate, distribution starts looking normal. If my distribution, if the data is or the sample size is adequate, so and I take a sample and I take a mean and I try to plot a graph. So slowly what happens, it will start looking normal. All right. So that is how it is. So it means that if my sample size is adequate, then I can assume that the distribution of the data is normal distribution, right? So that is the thought here. All right. So what we'll do, we'll try to look into this formula and we'll solve one or two problems. All right. So first of all, let's understand. So mean of sample mean always equal to population mean. Right? When I say always equal to, it's very close to the population mean. So that is what this guy is saying. Mu x equal to mu. It means that mean of samples equal to population mean. All right. And what is this? So here sigma, standard deviation, and x bar is a sample mean. So if I say that, okay, what is the standard deviation of a sample, then I can write this formula, that is sigma divided by square root of n. Sigma is a population standard deviation and n is basically sample size. If I apply this formula, then I will get the standard deviation of sample or sample standard deviation. As you can see here, mu is a population mean, mu, and sigma is a population standard deviation, this guy. Mu x a sample mean, this guy. Sigma x is sample standard deviation, this guy. N is a sample size, right? So that's how you can interpret this formula. All right, let's go to the problem statement and try to understand one problem here. So say that for a given mean 494 and standard deviation 100, what is the probability of obtaining a score more than 700? Right? So I was given a mean and also given a standard deviation. I need to find the probability of obtaining a score more than 700. So let's plot distribution, then interpret this problem statement. Right? So when I say a mean, always it lies center. Mu equal to 494. All right, and the standard deviation is basically 100. All right, so then what is the probability of obtaining a score more than 700? So when they say 700, so I can say that 700 lies somewhere here. This is a 700. Now I need to find the probability of obtaining score more than 700, this part. So what is the probability of scoring more than 700? That is the problem statement. I need to find the probability here. All right. So let's see how we can solve this problem. All right. So first of all, I'm going to import a scipy.stats as a st. Then what is mu? 494, that is given. What is standard deviation? 100, that is also given. And they have also given the x data. Right? So x data. And the formula is, in order to find the probability, so let's say that if x is given, this data is given, then I'm going to use a CDF function, cumulative density function, because we have a data from 0 to 1 and I need to figure out the data in this portion. If x data is given, I will use a CDF function. And what is that formula? Formula is basically st, this scipy.stats dot norm, normal distribution, dot CDF function. We know CDF function, in the earlier video we have understood, and the formula is x comma LOC, location is basically mu or the mean, comma scale. Scale is basically standard deviation. right? So this is the formula we have in order to find the probability if X data is given. We have X data, now I need to find the probability. So what I will do, I will use this formula and just plug in all this data accordingly. Then I will be able to find out the probability, right? So let's see how it is going to work. Sorry. Okay. So let's close this. So what I'm going to do, I'm going to import this and I'm going to execute very simple formula. There is no complex involved in that. Very simple, right? So what I got is basically 0.019, right? 0.019 is the probability, and the probability always lies between 0 to 1, right? And the question is, there is one more thing we need to look into this. There is something here, 1 minus. Why did I put that 1 minus? As I mentioned, it always starts from 0 and ends at a 1. That is how the probability will be calculated. So we have a 0 here. It starts from here and this is a 1. So whenever if I use only this function, what I'm going to get? I am going to get up to, from here up to this. This probability I will get. But the problem statement is that obtaining a score greater than 700. So I need this portion probability. So what I will do, I will say 1 minus whatever the data I'm going to get here, I will put it here. So that is what I have done here. 1 minus this probability, which will give up to this, and I'm going to subtract from 1, I will get this probability. That is 0.019. If you multiply with 100, you will get the percentage. Right? So that is how I will be able to use the CDF function. That is how I will be able to figure out the probability if X is given. So that is what I have mentioned here. The same thing what we have seen. When X is given, use CDF function to find the P. All right. So yeah, this is a simple problem statement. So this is how we will be able to solve the problem, or this is how we will be able to figure out the probability if the X data is given. All right. Let's understand one more problem statement here. So the problem statement is something like this. Mercury makes a 2.4 liter V6 engine, right? The laser XRI used in a speedboats. So there is a company called Mercury, which manufacture V6 engine, right? 2.4 liter V6 engine. So just like in our car and all, we get an engine, right? Like a 2.4 liter, 1.6 liter, V4 engine, V6 engine. Similarly, there is a Mercury which makes a V6 engine, which is used in the speedboats, like in the beach and all, right? I think everyone might have seen that. So in that speedboats, there will be an engine. So that engine is what Mercury is manufacturing, right? And the company's engineer believe that, okay, which company? The Mercury company engineer believes that the engine delivers an average power of 220 horsepower, right? Average power means mean. So how much he is saying, how much he is claiming? He is claiming 220 horsepower, 220 horsepower. And the standard deviation of power delivered is 15 horsepower. So he is claiming that the standard deviation of power is basically 15. So sigma standard deviation. Then what happens? A potential buyer, someone wants to buy it. right? Someone wants to start a business, speedboat business, and he want to buy, and a potential buyer intends to sample 100 engines, right? So company can say anything. Company can say that it is having a 240, 300 horsepower, whatever he can say, but the buyer has to test it, right? So because he is going to invest lakhs and lakhs of rupees in order to buy this engine, so he cannot simply go with his company's word, right? Whatever he is claiming, we cannot simply believe that. So for that, what he does, he intend to sample 100 engine, right? So 100 engine, he want to test it. So these guys are manufacturing maybe tens and thousands of engines, but a buyer wanted to sample 100 engine, and he want to test these 100 engine because he cannot test all the tens of thousands of engines. So he has taken samples of 100 engine. So samples are basically, I will call it as a n, and 100 is the number. And these samples will be run every single time. Each engine to be run a single time, right? Then only I will be able to understand the horsepower and things like that. So he want to run every single time all these 100 engines. So the question is, what is the probability that the sample mean will be less than 217 horsepower? He want to run that, and he claims that 220 horsepower, and he is checking. So what is the probability of this sample horsepower is less than 217 horsepower? So if the probability of 217 horsepower, if it is a less than that, maybe he want to cancel the order, maybe he don't want to buy, right? So that is what the problem statement here. So we need to find the probability that sample mean will be, these are the sample mean will be, these are running every time, the mean of this horsepower, right? So what is the percentage of that getting a less than 217 horsepower HP? All right. So that is what he wanted to test. So now what and all data we have? We have a mu 220, this guy. Standard deviation is also there. Yes. And sample also we have there. And we got a sample mean, right? We want to check a probability for a sample mean. So what is the sample mean? 217. All right. So now, whenever company engineer says something about his product, he always says that in terms of a population. He is not claiming for one engine or two engine, right? So he is a company engineer. He always talk in terms of a total population. He always talk in terms of a entire engines manufactured in his company, right? So it means that he is talking about a population, right? And the samples are 100 here. And we got to know that if the sample size is greater than 30, then we can say that if we can say that sample size is adequate, and we can say that data is normally distributed. That is what we have understood, right? Beginning of this session, right? That is what we have understood. If the sample size is adequate, which is greater than 30, then I can say that our data is normally distributed. So keeping that in mind, I want to find the probability getting less than 217 horsepower, which is a sample mean, right? Sample mean horsepower should be, if it is less than 217, and what is that probability, right? So that is the problem statement. Again, we are falling back onto the same kind of formula with a little tweak in it. All right. So now, again, X is given here, right? So again, I'm going to use a ST. Let's first of all, let's plot the distribution here. This is how is the distribution. And what is the mean? Mean, he says that 220 horsepower. Now we want to check for a 217. So I can say that it falls somewhere here, right? Let me shade this little bit. And I need to find the probability of this guy. And what is the standard deviation? Standard deviation is already given. Everything is there. And we know that probability always lies between 0 and 1. So here I don't need to do that 1 minus thing because we are looking less than 217 horsepower. All right. So what I'm going to do, I'm going to use the same formula, st dot normal distribution dot CDF cumulative density function, and here x data is given, right, and comma location, mu is also given 220, and scale. So scale, here we don't have a population sample standard deviation, right? We don't have a sample standard deviation because we are going to check the sample. So for that, what I need to do, I need to use some other equation here. Instead of using sigma, I'm going to use sigma divided by square root of n, right? So we know sigma for the population standard deviation, and in order to get the sample standard deviation, I have to use this formula, sigma divided by square root of n, right? We know n also, n is nothing but 100. So I can just plug in all this data. We have a sigma also, right? Everything is plugged in here, x, mu, standard deviation of a population, and sample size here, right? I'm just using np dot square root. So this will take care of that one. All right. So if I use all this formula and plug in those numbers, so let's execute this. I'm just going to replace with all this data directly, and it is giving me 0.22, that is a 0.022, and this data. So if I multiply with 100, yeah, you can get it in a percentage. So that is the probability of getting a sample mean, or the horsepower sample mean for these samples less than 217, right? So this is what the probability is, right? So that's how we can calculate the probability. And yes, this is all about this problem statement. All right. Thank you for watching this video. See you in the next video. Keep learning.